Hi, my name is Rob and I'm building a hypercar. And today we're doing a little different video than what you're used to from us. Today we're taking you behind the scenes to all the different projects we've got going on here. From design to materials to what we're doing with lights, with the wind tunnel, all kinds of stuff. So let's get started. So let's start with the design of the car and the optimization of the design. Let me first see if I know how to use a marker. So I'm going to use a whiteboard for that, so you'll see a lot of the back of my head. So what we have is we actually have a basic car design ready to go. It's very basic. And how was that developed? Well, I actually asked an AI, or a very simple piece of software, a very simple AI, to build me a car model based on the design we've talked about before. So we've got wheels, we've got the whole battery tray thing sitting there, we've got the motors in there, we've got suspension behind there, we've got people sitting in here, right, with seats, we've got a monocoque, we've got a front wheel with a motor and controller sitting in there. We've got some radiators. We've got radiators right here. We've got motor controllers right there. So we essentially made a 3D drawing of all the engineering elements. And we defined those elements in three aspects. That means they're either fixed, they're dynamic, and last, they're porous. And porous has two versions, in and out. So what we did is we defined what the car looked like from an engineering aspect. Where are the motors? Where are the people? Where's the battery? That's fixed. There's some things that are dynamic. For example, the suspension, the position of the wheels, because the front wheels turn and they all the wheels go up and down with the suspension. And then we've got areas that are porous. Air can go in or out, but with a certain resistance. That's where radiators come in, right? We've got radiators and we need outlets for those. This is the input to a simple design. What we essentially did is we told the computer, build a shape that encompasses that engineering aspect. Very basic. And just be as close to all the elements as you can. I can tell you it came up with some really weird design, but it came up with a design. Then I took that design and I have a system, a reinforcement learning is what it's called. Reinforcement learning. For those of you that don't know the term, this is how you teach a dog tricks. If it does something right, Fluffy, sit, you give him a cookie. If he doesn't sit, you don't give him a cookie. Well, the dog wants cookies. So he's going to figure out pretty soon, hey, if I sit down, when they say sit and I sit down, I get a cookie. Reinforcement learning, reinforce the good behavior. What I'm doing is I'm taking that shape, that outer shell that goes around all these engineering components, and I'm saying, now modify the shell. Move it up a little bit there and move it down a little bit there. And test it. Test both versions. So I've got this version. This one tests what if I move an element up. This one tests if I move it down. And I go test the performance of the car. So CD, CW, center of gravity, a couple other aspects. And I give that weight. I tell the system this one is more important than that one, more important than that one. And I do that in both. Well, then it tells me, well, it's actually better to do this movement. Great, so if I move this area up, it actually goes better. Great, let's use that as a basis and do that again. If I move it further up, do I move it further up by 1 millimeter, 10 millimeters? What gets better? And so on and so on. And every time I pick the right one and I go up and down. I do that hundreds of times, thousands of times with all aspects of the design. And then when we're done, we go back and we use another aspect of the design. What if I move that radiator a little bit? What if I set my preferences differently? After a while, I've got so much data that I can feed that into an AI that we're building ourselves. And for those of you that don't know, while I started in material sciences, I'm now doing computer science, have been for 30 years, and I design AI systems for a living. That's my other business. That's what I do when I'm not here. I'm designing our own AI system, a clustered AI system, to use that knowledge from calculating all those aspects to come up with an optimal shell for a design. So is it an AI designed shell? Maybe, not entirely. There's still a basis that a human designed. But it will be optimized to an engineering perspective. So we're not optimizing for making it look good, we're going to optimize it for optimal performance, whatever we define optimal performance to be. We have this aspect mostly done. We have the first drape of that kind of there. It's really bad, so kind of hesitant to show it to you. We've got the first test of running that in a distributed system. And there, of course, is the other aspect. All of the things we're doing, we're going to put this in open source. When this is done, when we've got a working prototype, we'll put that on GitHub or maybe some other platforms under a permissive license and let you use it and build on it or go from there. Also, to do all this work, we're using FreeCAD as our design software. And from FreeCAD, we're doing all these calculations in OpenFOAM. So we're doing FreeCAD for the design part and using the Python library of FreeCAD to make those modifications. So using Python, we'll actually be able to make those modifications. So we're using Python to change the model. Then we're using FreeCAD Design and the plugin for OpenFOAM. So we've got the FreeCAD OpenFOAM installer. We'll do the meshing. Then we'll send it to OpenFOAM for the solver. Out of that come our numbers. And we will compare that, and based on that, go back to FreeCAD. Why am I telling you this? Well, all these aspects, FreeCAD, OpenFOAM, the solver, the Python, it's all open source. You could do this yourself. So again, technology we're developing that we will be able to give to the community and you'll be able to build up on. Is this done yet? No. Do we have certain aspects already worked out? Yes, we do. Is it working from a concept? Yes. So the concept has been proven, but we're not far enough along yet to be able to show you what it is. Now we're currently talking to a designer that will help us do the looks of the car. But I'm not entirely confident that we'll be able to strike a deal with that person, and that has to do with intellectual property laws. The way the laws work, if I have someone externally develop that design, they always have some rights to it. And for me, it's very important that I can put all of it in open source. So even if I hire external people, I'd gladly pay you, I'll gladly pay a designer, but I want to be the full owner for now and in the future and be able to put the design in open source. So you, me, anyone else can use that design as their basis for their car in the future. And that doesn't seem to be all that possible. So doing some pretty complex things here. Obviously this takes a while. It's kind of hard to show you every aspect. We'll be making a video on it here in the next month or two, I think, hopefully. That will show that in more detail and will show the different aspects, maybe every 10th iteration, what the car does and what the wind tunnel simulations for that site are, because using this in OpenFOAM will do a CFD analysis, computational fluid dynamics. We're actually going to be calculating what the wind tunnel will tell us. So we're going to predict what the wind tunnel will tell us. Based on that calculation, we'll then make a model on the CNC machine and put that in the wind tunnel to try it out. It's getting there, but we've got some steps to go before we're confident enough to give it to you, so you can take that next step. Hopefully that gives you a little bit of an idea of what we're doing with the design of the car and how serious we are with that. This same concept will also apply to the suspension, so the active elements of the car. how will the suspension work? We'll put that through the same type of calculations and the same type of optimization. Haven't found the right open source tools yet to do that with. So if you have ideas on that, please let us know. We would be gladly listen to you or work with you to get those tools open sourced so we can build those capabilities. So for our next project, we're actually planning things for the CNC mill. So CNC mill, you've probably seen that in prior videos. Right now, I've got a temporary hookup with just a Dremel tool, which is about as basic as it gets with a long cutting bit in there. But obviously, there's way more things we can do with that. We can mount a router in there, so more powerful. The Dremel can only take 1/8" bits. This one can take up to 6mm. So that means we can put some bigger cutters in here and do bigger surfaces and move material that much quicker. So planning to make both of those capable to hang in there. But obviously we have way more capabilities. So for example, what I've got here is a pretty good in-head extruder printer head. Well, we're also going to make that compatible with the machine. And at that point, we've got a huge surface area that we can print on. The table won't be heated, so we'll have some adhesion problems there. And we'll have to work on that. But we could preheat the table maybe, just with an external heater. We'll have to figure out how to make that happen. Just took this off of a other printer I built years ago. This should be pretty good. It's also got a quick mount system, a quick detach system, so that works. Obviously that needs a pretty solid power supply, so that's ready to go. The part I don't have here yet, but I can hear you guys screaming at the monitor while I'm building this. Obviously a laser in here would be no problem at all. And then of course on top of that, it needs a suction system. Well, we've already got the big vacuum sitting here. We'll use that as a suction system, and I might pipe it to go directly into the trash. I might pipe it to go directly into the trash compactor, so we can easily keep going, compact, and keep going one after the other. The other aspect of it, and that's a little harder I think for the camera, it will create fumes, especially when we go to laser. Obviously the fumes are pretty nasty, you don't want those in your work environment. But if you look here, there's ventilation shafts here that go to a central cleaning system, air filtration system that goes outside. So we will also be hooking up this whole setup to that ventilation system and obviously running the ventilation system when we run the CNC mill. So obviously this is the wind tunnel fan housing. It's huge. Still tweaking things on that. But next thing is going to be the test chamber on top here. Most of the wood parts for that are already cut. The glass is actually sitting in the back. I showed you that at the end of the video where we built this whole setup. But there's a lot more aspects of that test chamber that we're working on. So let me show you some of those. In the floor of the test chamber of the wind tunnel, there'll be a lot of sensors. Obviously there'll be wind, airspeed, temperature, things like that. But we also have to measure the object that's in there. So we do that with weight sensors. So there will be a weight sensor on every corner. And all of that will be in a circular platform that can rotate. So we can rotate the car. So we measure with these 4 sensors. When the wind comes in from the front, we measure downforce. How much does it pressure left, right, front and rear on the wheels? Then that whole thing will be on a platform that can rotate. And that platform will be measured using strain gauges, and it will measure how much pressure is on the car or on the object we're testing in reverse. So it will measure how hard the wind pushes on the car. And that combination will give us lots of information about the design of the car, or the spoiler, or the setup, or you name it. And that will help us optimize the design. Now obviously all those parts need to come together in a pretty comprehensive and complex mechanical setup. So let's go upstairs and I'll show you the CAD. So welcome in my workspace. As you can see, we've got an office too. So here's the CAD design for the wind tunnel design. So what you see here is the bottom plate of the test chamber of the wind tunnel. So let me at least take that away, so it's no longer there. Also take the second plug away. Here is the platform that the car will be standing on. So let me undress it a little bit. So now the top plate is gone. So here are the 4 sensors that you can see that we just showed you that the car sits on. This is actually now scaled to a 1 in 10 car, so a very big one. The one we showed you downstairs is a 1 in 24, so the sensors will be closer together. So there will be versions of this platform for every scale and every object we want to measure. So there's 4 sensors there, and then that whole platform is actually floating on top of 2 of those strain gauges I just showed you, right here and right there. So this one and that one. And one measures pressure going back, so straight back in the direction of the airflow. So the direction of the airflow in this case is from right to left. And the other one measures strain the other way, so side to side. And why is that? Well, because it all sits on a platform. The bottom is actually solidly mounted, and that platform, the whole platform, can rotate towards the base. So we can actually rotate the car as it's sitting in the wind tunnel as we're testing the whole environment. A pretty complex setup, and there's actually a couple of more spaces. So let me show you something more. So if we turn on every element again, so let's also put a car in the wind tunnel. As the air is moving from right to left, there's first a slot in the bottom plate. We use that to suck air out because laminar flow air comes in, but obviously because it's right against the bottom plate, it will start shaking a little bit. It will start moving a little bit. Here we just put a little bit of a vacuum on that hole to take a little bit of the air out and to make sure we have perfect laminar flow also going underneath the car. Then we have the car on the platform that can rotate. But there's a second space behind it that can also have the platform. We can actually move this platform in this position or in the position in the back. And what we can do then is we can put a car in front or a car behind, and we can test what happens when there's drafting, or I don't know, there's something else in front. What happens when you're close to a wall? What happens when you're close to a barrier? Or something is in front of you, or multiple cars in front of you. What if there's 2 cars and you're right in the middle of them? What happens? What's the balance of the vehicle? All of that we would be able to test in this wind tunnel with a setup like this. I'm not 100% sure if we're going to do it like this or going to make the whole section here, a square section of the bottom of the wind tunnel, drop out and move it somewhere else, because that gives us a little bit more flexibility. So design is still out on that. So there's another option for that element that we can do in the area where the car sits, but for that we need to go downstairs, so I can show you there. So back downstairs. So we've talked about the whole sensor platform that rotates and does all kinds of fancy stuff. Well, there's something else we can do with the floor of the wind tunnel, and that's this. Some of you might recognize this. This is a treadmill-based 3D printer. Tried several things with it. I'm not very happy with this. This is not the way I want to print things, but the treadmill is actually kind of interesting. It's fast, it's very controllable, it's driven by steppers, so you can actually control the speed very well. And what I'm thinking of doing is putting this in the floor of the wind tunnel to make a rolling road wind tunnel. And what's the difference? Well, obviously in the setup that we just discussed, the floor is standing still while the wind is moving around it. Well, I don't know about you, but if I'm standing still in my car and the wind hits me from the front, that's a completely different sensation than if I'm driving in my car, because then the wind is moving, but the road is also moving. It's moving at the same speed as the wind, because I'm driving along, assuming there's no wind coming from another direction, I'm driving along on the road. So what we can do on here is we can put the car on the treadmill, have the wind come from the front and rotate the treadmill while the wind is going, so match the speed. So the car will have the full sensation as if it's driving. And in that way we can actually show what happens when the wind is also pulled along by the rolling road. Now on top of that we can do some other things. If I rotate this around a little bit, there's actually some areas here that still have some 3D print on it. What if I put some hot glue on this treadmill and create obstacles? What if I make a road that's a little bit bumpy and the suspension gets to work, or the car rotates a little bit? What does that do to the aero of the car and the stability of the car? We'll be able to test that by putting this treadmill, this rolling road, in the bottom of the test chamber. Now obviously when we have this rolling road, we won't have all those separate sensors, because it's just not possible to have a rolling element, so a moving thick piece of material on top of those sensors. It will just give you sensor readings that are completely incomprehensible. So there'll be fewer sensors, but we can do aerodynamics, we can put the smoke machine on there, we can do all kinds of other aspects. So it's a nice way to test. In the test chamber of the wind tunnel, we obviously are going to put smoke on the object, and we want to really have details on how that smoke moves. So we want high performance, high speed cameras on that. The camera we're using here will do 4K high resolution video at 60 frames per second, but I think we want to go higher, way higher than that. And to do that, we need lots of light. So follow me along. So we're actually building our own light. There's a 3D printer piece printing right now, so we'll get back in a minute when that's done and show you how that works. But this is actually a very bright light that will sit on top of the test chamber and will allow us to really highlight the object that we're testing and see the smoke really well. So let's see if it works. I've got a power supply right here and it's set to 12 volts. These lights are actually 3 volts. So what I do is I've got 4 of them in parallel, and then 4 sets that are in series. So because I've got 4 of them that are in series, it's 4 times 3 is 12 volts and 4 of them in a row. So it uses quite a bit of power, but nothing too crazy. So let's hook this up and let's see what it does. Well, as you can see, that's a pretty good bright light. We will be able to put this on top of the test tunnel, on the window there, and really directly light the object, see the smoke and see all the details of what we're testing. That's very important to be able to see exactly what's happening in the wind tunnel, because it's going to be happening at really high speed. So as you can see, it's running at 12 volts and 2.8 amps. So let's say about 3 amps. The power supply can actually deliver much more. So the fact that it's limited to about 2.5 amps, 3 amps, let's make it 3 amps, means that we're using 3 times 12 is about 36 watts of power. So that's pretty low. So this means we have 12 volts at 3 amps, that's 36 watts of power. Well, that's not huge, but it's enough. So that's why I've connected all these lights to these huge cooling fin, so we can get rid of that heat. Because obviously we don't want the heat to shine down too much, because it may crack the window. This way, this should be plenty to get rid of 36 watts of heat. I had this thing left over from some project in the past, so I just grabbed it. The shroud is printing right now, so I'll be back with you when the shroud is ready and put that on, and then we'll test how this works with a car under it. Well, it's done, so let's get it off of here. Let's see if the light fits. Let's see if I measured it correctly. We got the light, we got the base. Let's see if it actually fits together. Looks like a pretty decent fit. If it clips in, that's usually a pretty good indication. So the light in this test setup, just because it's nice to play around and see what it's actually going to be. Put a little model under there, Mercedes 300 SL, how can you go wrong? Got a power supply, so let's try the light. Well, that obviously works pretty well. Now I think you can already see the smoke is already going. So let's turn the smoke generator on. I've actually got a foot switch here to turn that on. So that's more or less how the wind tunnel is going to look. The air movement will be a little faster and a little bit more laminar. So let me tell you a little bit about a project that's still early on, but definitely has some major impact on what we're doing with the car. And that is the material we're going to be using to build our car. And you're going to say, well, you said it was going to be carbon fiber. Yes, it is going to be carbon fiber, but you got carbon fiber and you got carbon fiber. There's way different scientific concepts, mechanical capabilities between one or the other. And we actually want to go a little bit further by using carbon nanosheets to optimize what we're doing. So I've got some props for this video. So this is just a string. But essentially, carbon fiber, if you look at it in detail, is just a bunch of really thin strings. Strands of string that are sitting next to each other in a matrix of some kind of epoxy. So, by the way, I'm really bad at drawing on the whiteboard, so bear with me. So we've got carbon fiber, lots of strands going every which way, right? And we lay them up in different directions, so we get a nice matrix, but it's one layer on top of the other. Then we do maybe a 45-degree layer. But as we all know, there's plenty of examples of this. If you have an impact at any point, or you have a larger impact, or it starts to tear on the side, it actually has really bad impact resistance and even worse shear resistance. Shear is how two things are together that they tear, because it tears between and even across those different strands of carbon fiber. It is not very strong. It's not very resistant to that. If you, for example, look at an aluminum bodied car, it deforms, right? It crushes in, while carbon fiber pretty much explodes. Even a fiberglass car deforms much more than a carbon fiber car. There's nothing to be done about that. It's really strong, and really it's the nature of what it is. Now, obviously, this is a little bit bigger than the actual carbon fiber. This would be zoomed in. Well, what if we even zoomed in even further? There's actually something we can do to make this better. And that's why I've got these patches as an example. What we will be doing is, at least this is the theory, and it's not there yet, we will be placing on the outside layer random pieces of carbon nanosheets. And what are carbon nanosheets? Well, carbon fiber is a strand, and that's actually made up of a long polymer of carbon elements, carbon atoms. Carbon nanosheets are nice matrices of carbon, essentially a diamond, but two-dimensional, so a very flat diamond. It is a perfect matrix with connections every which way, so really strong. And I know this is not the way it actually works. Material scientists and chemists can tell you way more detail, but I think it goes too far for this video. But we will be creating this perfect matrix of carbon elements. So it's a sheet, just a few atoms thick, of carbon. And those are actually really good in resisting impact and even better in resisting shear. And we will be putting those in the outer layer that we put either the coating or the outer layer of epoxy on the carbon fiber. And what will happen? Normally, if you have a tear, let's say we start tearing from here, it will tear through. It will get to this nanofiber sheet and it will stop. It will stop on the edge here. So if you put enough of those close by, if you have an impact here, well, it will start radiating out, but it will stop once it hits the nanosheet. So if you do enough of those, it will get so strong that it will actually resist shearing, tearing, and coming apart. We've done some modeling on this. Actually, I have, because guys, this is my background. And if we inject 0.3% by weight carbon nanosheets in the outer coating of our carbon fiber parts, we'll be able to improve the shear strength by 50 to 80% improved shear resistance. That's huge. Now this theory, it's not there yet. But let me show you with a little example of how this is supposed to work. So, hopefully this shows something. It's just a piece of printer paper, right? Nothing special. But if I tear that, it tears really easy, right? It's actually fairly strong, but it tears really easy. Well, what happens if I put a piece of tape on there? So that piece of paper is almost, let me at least make sure the tape is on there. So the paper is like our carbon fiber part, and the piece of tape is like our carbon nanosheet. And what happens now, if I start to tear it, and the tear gets to that, it actually won't tear any further, it will stop the tear. The tear resistance could increase immensely by putting that piece of tape on. That's the same concept that we're doing here. Just makes the material that much stronger. What we're currently in the process of, we're planning our own fabrication of carbon nanosheets. And we're doing that by using a tungsten and a carbon rod under high voltage, high amperage. So think about an 100 amp at 60 volts, creating an arc between those two in a water bath. That water will be flowing, will actually be circulating, and we will filter out of that lots of carbon debris and carbon nanosheets. Those nanosheets we will either, and this is a question mark, be using as a coating or in the outer layer of epoxy at about 0.3% by weight. And that should generate our results. Now obviously this is not standard, but you can't go buy carbon nanosheets at the DIY store. I can't even buy them at my local lab environment. This is pretty complex science. This is fairly new. It has been theorized. I haven't been able to find any example of someone actually doing this, but the theory is solid, in my opinion. This design is done. I've got a design ready for that. We're currently sourcing parts, and in the next couple of months we'll be trying that. This is obviously in parallel to us building the design of the car. We think doing this will increase the strength of our carbon fiber and make the car body we're producing that much stronger and that much more resistant to impact and shear, which are the two major failure points in a race situation. So we will be doing that in parallel to building the car and the design and start building the mechanics. We're early on in this process, but I'm fairly confident this is going to work. So any ideas on this? You want to collaborate? You've got some research that you think applies? Let us know in the comments and we would gladly hear your input. So I hope you enjoyed this episode. Obviously we went from trash compactor to really cutting edge engineering and science. So there's a little bit for everyone in this video, but hopefully this gives you an idea of what we do every day and how we're slowly, really slowly, working towards building that hypercar. Because building a hypercar is not just ordering some parts from the local car place and just putting them together. It is a lot more involved than that. So we're building the infrastructure, building all the parts, everything we need to start actually building a car. Hopefully you enjoyed it. If you did, like, subscribe, comment, give us feedback. If you have any ideas about any of the project, hey, we're always interested to hear from you. Thank you.